Hi, and welcome back. We are going to cover section 10.3 today, where we are simplifying radical expressions. Now, a couple key items with radical expressions, and that is we must have the same root index to be able to use a product rule. So, our first rule of the day, product rule. That is saying that if I have two radicals being multiplied, they must have the same root index of n, for example, to be able to combine these into a single radical expression of n, the nth root of ab, the product. Now, what this is going to actually look like is something like, let's say, the square root of 5 times the square root of 7. If I were to combine these, that would be the square roots, since they both have the same root index of 2, it's implied. So I could have the square root of 5 times 7 and simplify it. And if that helps me to get to a value that I could do a square root, that would be great. But in this case, 35 does not break down because both 5 and 7 are prime. So that is my end result for a simplified expression. What does it look like if I have variables? Well, let's take the square root of 10y, multiply it against the square root of 3x. What you're going to do is simplify it by combining. They have the same root index. You have the square root of 10 times 3 is 30. Y and x, so you have xy. And that's it. Pretty straightforward, actually. What if it's a fraction? Something like this, for example, where I have the square root of 5 over a times the square root of 11 over z. Well, just like you would multiply fractions, you go straight across. You already have the same root index, so that's perfect. You can combine these into a single square root. 5 times 11 is 55. A times z is az. And there you are. Now, radicals also have a quotient rule, and it works pretty much the same way. So this is your product rule. Your quotient rule is basically looking at it as the nth root of a over b, and it can be split up so that you have two identical root indexes where you have a over b, just like so. Now, this is sometimes very helpful. For example, let's say I have the square root of 16/25. Technically, I can split this up so that I have the square root of 16 and the square root of 25 separately. And that helps me because it does allow me to look at each individual component in its own separate form. This works out very nicely to 4 over 5. If I were to have, say, the square root of 100 over 81, you may not be willing to really go through and write those fractions all the way out, but you could easily say, I know the square root of 100, I know the square root of 81. Taking those separately, I get 10 over 9. Pretty easy to use. Now, you might be saying, well, I've already been doing this. Why is it any different than what I've already been doing? Well, you may not have seen a problem like this so far, where you have the square root of 11/25. There is no square root of 11 that you can easily get, so it would come out to a decimal value. So you'd have to have the separation of the square root of 11 and the square root of 25 to be able to then say, I have the square root of 11, can't do it perfectly, so I'm going to leave it. The square root of 25 is 5, so I can do that. So that's what I get as an end result. Cool. So my end result actually can contain a radical value. And that is perfectly fine. In fact, that's very normal, actually, as you're working with radicals. So let's do a couple more. Let's say I have the square root of y to the 8th divided by 16. You can split them up separately. Square root of y to the 8th, square root of 16. That's y to the 4th over 4. How about the square root of x to the 6th y to the 4th over 64. Sure, you could still split this up. You could technically split it up even as a product rule up here in the numerator if you needed to, just kind of working in reverse, so that you're looking at each individual component. And you can do this because everything is currently in multiplication or division. So I'm using that product rule to split these up, and I'm using my quotient rule to split my numerator and denominator. So I'm looking at each individual component. This is x cubed, this is y squared, and this is going to be 8. Square root of 64, 8 times 8. All right. Now, my next one is showing you how you can actually utilize this together. So I'm going to get a little more room there. So I have square root of x to the 5th y to the 11th divided by the square root of xy. Now you're looking at this and it's like, whew, I got some pieces here. It's crazy. They have the same root index. So I can technically combine this into a single square root, looking at x to the 5th y to the 11th over xy. I can then simplify in here before taking the radical. So let's do that. Thinking of my quotient rule, x to the 5th, x, that's going to be x to the 4th. Y to the 11th and y, that's going to be y to the 10th. And I still have the square root. Now I can take the square root and I can think of those separately if I needed to. Erase this so we don't run into this problem. And so this would technically work out to x squared y to the 5th. So you can work wax on and wax off, forward and backwards, using your quotient and product rules interchangeably as you see fit through the problem. Now, let's talk about how this applies to simplifying square roots. If I gave you the square root of 24, the square root of 24 does not have a perfect square root. If you were to try to pop it into a calculator, you'd get 4 point something something something. And you can know that because square root of 25 is 5. This isn't quite there. It's just under that. It's just shy. So what do you do? Can 24 be broken up so that you do have a perfect square root that can be pulled out? The answer is yes. 24 can be broken up into 4 times 6. 4 has a perfect square root, so I can pull that out. That's going to be 2. Now, the 6 doesn't break down into a perfect root. It's 2 and 3 once you actually break it down, so leave it alone. You have 2 square root of 6. Now, if you were to look at this in a fully expanded form, I actually showed you the shorthand version of doing this. If you were to look at this in a fully expanded form, you would actually say, okay, 24 is 4 times 6. That's technically 2 times 2 times 2 times 3, right? And I'm looking for a pair of numbers. That's why this is an implied 2 out here. There's my only pair. So my only pair was pulled out. What I'm left with was what I'm left with here. So it's just easier to see where those perfect values are as you're breaking down your multiple pairs, and then pulling those pairs out. Or if you're dealing with cubic roots, pulling out those 3 of a kind, or 4th roots, 4 of a kind, 5th roots, so on and so forth. You get the idea. So let's look at 32. Square root of 32. Well, it's not a perfect square root because the square root of 36 would be 6. You know the square root of 25 is 5. So it's in the middle there, right? So it's a decimal value. But you could split this up into 2 times 16. There is a perfect square root for 16. So we're going to pull this out as 4. And I'm left with 2 inside of the radical still. So I have 4 square root of 2. What about the square root of 45? Well, technically, the square root of 45, you could do the same thing. You have 9 times 5. There is a perfect root of 9. That's 3. You're left with 5, so that leaves you square root of 5. 3 square root of 5 would be your end result. How about the square root of 300? Sounds like a lot, right? I don't know the square root of 300 off the top of my head either. So I'm going to split it up. I have 100 times 3. 100 can be broken up, so that's 10. I can't do anything with this 3, so that's 10 square roots of 3. Cool. How about the square root of 10? Huh. I don't know. Let's see. 10 could technically be broken up, right, to 2 and 5. Oh, you can't do anything with 2 or 5. So the simplest answer here is square root of 10. So sometimes you can't actually break up your roots, and that's okay. That is left as a radical. But if you can pull a perfect square root out, you should. So here you could pull out a 10 from this 100. Here you could pull out a 3 from this 9. Here you could pull out a 4 from the 16. And so you pulled those values. What you're left with each time is what you're ending up with in your radicand value. It's that little attached component, if you will. Okay, let's try a couple more just to get some good practice here. I have a negative square root of 48. Remember, that negative is not applying to the radicand. That negative is completely separate, so don't drop it, just carry it over. 48, what can it break down to? Some of you might be like, well, 6 and 8. Okay, let's say you do that. Let's say you don't see a perfect square right off the bat. You see 6 and 8. It's a pretty common pair that I get whenever I ask this question. Well, 6, that's not a perfect square. 8, that's not a perfect square. But can they break down? Sure. Let's look at it if it breaks down. I want to show you this process of having to go through and find your pairs or find your roots in case you run into a number that you're not familiar with. So 6 is 2 and 3. 8 is 2 and 4, right? Hey, I know 4 is a perfect square, so I can take that out. And I also see that I have a 2 here and a 2 there. I got a pair of numbers. So I can pull 2 from this 4, and I can pull 2 from this pair. I don't have anything to do with 3, so I still have 3. Don't drop your negative. So this is 2 times 2, that's 4. That's a negative 4 square root of 3. And this is a perfectly acceptable way of doing it. Perfectly acceptable. Is it the easiest way? No. But this is how you could encounter a problem if you're not seeing the perfect square right off the bat. Now, if you were to look at the same exact problem, I'm going to rewrite it right here, negative square root of 48. If you were looking at this problem and you're like, hey, I see a perfect square of 16, and that's times 3. This 16 is 4, right? Once you pull it out. It's the same exact thing, just a little less work. So either way, you can go through, you can break down to get all of your little factor pairs and see what you can pull out, or you can see if you see perfect squares or perfect cubes or whatever it happens to be to match that root index and pull those values out as well. All right, let's try just a couple more. That was number 6. Here we are. So square root of 16m cubed. Ooh, 16, perfect square. Pull it out. M cubed. Yikes. What do we do with m cubed? Well, m cubed is technically m squared times m, isn't it? Now you might be saying, well, why did you split it up that way instead of writing m times m times m? You absolutely could. But I'm looking at an even root index of 2. This is divisible by 2. So that means I can pull this value out. That's that power over root in use here. So that's 4m, the m coming from here. This m has a power of 1, so it doesn't really do me any good. So I have a square root of m left over. Let's try another one, similar to that one. So I have 200 k to the 7th, q to the 8th under the square root. 200. Well, I'm going to look at that as 2 times 100, because I have a perfect square with that 100. K to the 7th, I'm going to write that as k to the 6th times k. Q to the 8th, I like that one. I'm just going to leave it. Because I have a root index of 2, I'm looking for pairs, and I'm looking for exponents that are divisible by that 2 value. So I can pull out a 10 from here. I can pull out k to the 3rd from there. I can pull out q to the 4th from there. What am I left with? 2k. So I'm left with a square root of 2k here. So I have 10k to the 3rd, q to the 4th, square root of 2k. And that is my simplified version of that problem. Okay, let's do the last problem here. I encourage you to go through and get lots of practice in this section, because honestly, it's very easy concepts, but it does take a lot of practice to really get a good handle on it. So that being said, tackling this last problem, what would you do first? I'm looking at a square root. I have 25p to the 7th. I'm going to say let's split it up. So I have the 25, I know is 5 times 5. I'm just going to write that as 25. I have p to the 6th times p. That's the one that I needed to see split up, right? Square root of 25 is 5. Square root of p to the 6th is p to the 3rd. I'm left with p in the radical. And there you go. Okay, guys, that is it for section 10.3, where we were simplifying radical expressions. We're going to continue into section 10.4 in just a few moments. Catch you later.